So what actually happens when a single, seemingly minor node in a massive supply chain just fails? We live in this deeply interconnected world, right? And the reality is, the failure of one small business can literally bring entire global industries to a grinding halt. Understanding that exact fragility is the fundamental problem we're going to solve in this explainer.
We call this cascading failure the domino effect. It's like a giant puzzle where pulling out one piece ruins the whole picture. The economic failure of just one entity propagates immediately to both its direct and indirect connections. So buyers connected to that failing entity, they're adversely impacted because they suddenly lose access to crucial products. But at the exact same time, suppliers connected to that entity are hit too, because they lose revenue from lost sales. Basically, one falling node takes down both buyers and suppliers in a devastating chain reaction.
Welcome to the Explainer. Today, we're exploring the technical solution to this massive economic vulnerability by using graph data science to mathematically quantify network risk. We'll be looking specifically at how organizations are modeling risk in supply chain networks using knowledge graphs and the Neo4j Graph Data Science library.
To get there, we've got a 5-part roadmap. We'll cover the supply chain domino effect, graphing this supply chain, PageRank and entity importance, reverse PageRank and vulnerability, and finally, calculating total risk scores. Let's jump right into Section 1, the supply chain domino effect.
Now, to model risk accurately across a network, we first have to categorize our entities. We classify every business in our supply chain into one of 3 distinct categories to build a solid framework for our math. First up, vulnerable entities. These are your bottommost tier in the network, mostly small businesses supplying parts or subassemblies. They are highly likely to fail if a connected entity fails. Second, we have important entities. These are the top-tier ultimate buyers who assemble the finished products. If an important entity goes under, it sends shockwaves across the entire network. And third, we have critical entities. These are the rare businesses that actually register as both vulnerable and important at the exact same time.
Moving on to Section 2, graphing the supply chain.
Okay, let's dive into this. To move from the physical reality of a supply chain into a purely mathematical model, we construct a homogeneous knowledge graph. We use a single company node type, which can represent a supplier, a buyer, or both. The relationship connecting these nodes is simply labeled supplies. And this relationship captures absolutely crucial semantic information because it holds properties for both the dollar volume of the trade and the total count of orders. This brilliant structure allows us to measure the exact mathematical strength of the relationship between any 2 entities in the chain.
And when you visualize this data, it instantly reveals the massive scale and complexity of the actual network. You really start to see the deep interconnectedness of all these entities. Nodes are constantly supplying other nodes, creating this vast, tangled web of interdependence. But here's the thing. This global information is exactly what we need to analyze to locate those hidden risks.
Which brings us to Section 3, PageRank and entity importance.
To identify the most dangerous potential dominoes in our graph, we deploy the PageRank algorithm from the Neo4j Graph Data Science library. PageRank is a global centrality measure. It calculates the importance of a node based on the importance and number of its connected neighbors. What's cool is that it dynamically estimates importance using the entire network's global information, not just local degree centrality. A company is literally only as important as the companies that supply it, which makes PageRank a natural fit for evaluating supply chain influence.
Now, what's really interesting about this slide is how we interpret PageRank depending on the network we're looking at. In traditional web search, a high PageRank means high influence. It's a great thing that bumps your website to the top of Google. But in our supply chain network, high influence translates directly into a high potential for triggering the domino effect. An entity with a high PageRank score represents an enormous risk, because if it fails, it's going to devastate that vast network of suppliers feeding into it.
So we execute a Cypher projection factoring in those relationship weights, like dollar volume and order counts, and then we run the PageRank algorithm. The results are normalized on a clean scale of 0 to 1. And look at this. Our query reveals that General Cars Inc. registers a perfect normalized importance score of 1.0. Stanley Steel comes in second with 0.727. Mathematically speaking, General Cars Inc. is the single most important entity in this entire network.
When we drill down into General Cars Inc., it becomes super obvious why it holds that maximum score. General Cars Inc. is a Tier 0 ultimate buyer. Even though it only has 2 direct inbound connections, those Tier 1 suppliers are fed by highly significant Tier 2 nodes, which are fed by Tier 3 nodes, and so on. It's this deep nested structure that means if General Cars Inc. were to fail, it would cause the absolute maximum number of dominoes to fall across the network.
Next up, Section 4, Reverse PageRank and Vulnerability.
Let's move to and see how this builds, because now we're shifting our focus from the entities that cause the disruption to the entities that suffer from it. To calculate vulnerability metrics, we have to create a directed graph with reversed edges. We literally take our original directed supply chain knowledge graph and flip the direction of every single relationship.
By running some straightforward Cypher code, we generate these reverse edges, but we label them buys instead of supplies. And these new buys edges inherit all the exact same properties, volume, order counts, from the original edges. This creates a brand new graph projection that is specifically designed to run the reverse PageRank algorithm.
We run PageRank again, but this time exclusively on the reverse graph, and these results identify our most vulnerable entities. Pfizer Equipment maxes out the vulnerability score at 1.0. Boston Scientific follows closely at 0.844. These are the bottom-tier suppliers that are overwhelmingly likely to fail if a disruption happens anywhere above them.
Putting them side by side perfectly contrasts the two extremes of our network. On one side, you have General Cars Inc., the top-tier buyer whose failure crushes everything beneath it. On the other side, you've got Pfizer Equipment, the bottom-tier supplier with numerous outbound connections to buyer nodes. Pfizer Equipment is basically sitting right in the crosshairs, the entity most likely to be crushed by a falling domino originating anywhere else in the chain.
Finally, Section 5, Calculating Total Risk Scores.
So the crucial point is, how do we synthesize these two distinct models into one single metric? We define criticality. A critical entity is a node that registers high scores in both importance and vulnerability simultaneously. Think about it. A truly critical entity is both a heavy domino that can crush the network and a vulnerable target standing right in the line of fire.
We combine our findings into this beautifully simple equation. The final risk score is just derived from the arithmetic average of the two algorithms. We take the importance score from PageRank, add the vulnerability score from reverse PageRank, and divide by 2. It's that clean. This gives every single entity in the network a definitive, mathematically sound total risk score. And this brilliantly illustrates the power of graph data science way beyond just basic analysis. These extracted risk scores serve as vital node attributes for downstream machine learning tasks, things like link prediction or generating node embeddings using graph neural networks. Plus, you can seamlessly leverage this exact framework to uncover risk in completely different domains like crypto fraud, money laundering operations, and complex tax evasion networks.
Because let's face it, every complex system contains hidden vulnerabilities just waiting to trigger a systemic collapse. But by treating your data as a highly interconnected network, you gain the ability to mathematically quantify those threats before they ever materialize. So, I'll leave you with this. How could these knowledge graph centrality algorithms uncover the hidden risks in your industry?